Welcome, everyone. Today, we'll dive into an essential step in the machine learning workflow, validating a model using a validation dataset. Imagine building a model to predict voter turnout in an election. It performs perfectly during training but completely fails to predict real-world outcomes. Why does this happen? Often, it's because the model hasn't been properly validated. Validation is how we ensure that a model not only learns patterns from the training data but also generalizes to unseen data. In this lesson, we'll explore what a validation dataset is and why it's crucial for building reliable models. Let's start with the basics. What exactly is a validation dataset? A validation dataset is a subset of your data that's separate from both the training data, which the model learns from, and the test data, which we use to evaluate the model at the very end. The role of the validation dataset is to help us measure the model's performance during development. Here's how it typically works. When you have a dataset, you divide it into three parts, one for training, one for validation, and one for testing. The validation data acts like a checkpoint during the modeling process. It gives us a way to see how the model is performing before we finalize it. This is especially important because, during training, the model can become too focused on the specific details of the training data, a problem known as overfitting. The validation dataset helps us catch this early and make adjustments. Now, why is this process so important? Think of it this way: if a student only memorizes answers from a practice test without understanding the material, they might ace that specific test but struggle on the actual exam. Similarly, a machine learning model trained without validation might perform well on the data it's seen but fail miserably on new data. Validation is what ensures the model isn't just memorizing patterns but actually learning. It's a critical step for evaluating whether the model is overfitting, focusing too much on the training data, or underfitting, meaning it hasn't learned enough. It also helps us fine-tune the model settings, like choosing the right learning rate or the number of layers in a neural network. Without validation, it's impossible to know whether changes to the model are truly improvements or just lucky coincidences. And the implications go beyond technical success. In real-world scenarios, like predicting policy outcomes or understanding public sentiment, deploying a poorly validated model can lead to flawed decisions and significant consequences. Now that we understand what a validation dataset is and why it's so important, let's explore some of the techniques we can use to validate a model. One of the simplest methods is holdout validation. In this approach, we divide our dataset into two parts, one for training and one for validation. For example, we might use 80% of the data to train the model and reserve the remaining 20% for validation. This method is quick and straightforward, but it has a downside: it might not capture the full variability in your data. If the split isn't representative, your model's performance might be overestimated or underestimated. To address this, we have k-fold cross-validation. Instead of a single split, this method divides the data into k subsets, or folds. The model is trained and validated k times, using a different fold for validation each time and the rest for training. This ensures that every part of the data is used for both training and validation, providing a more reliable estimate of model performance. However, k-fold can be computationally intensive, especially with large datasets or complex models. For datasets with imbalanced classes, like when predicting rare events such as fraud or policy violations, we use stratified k-fold cross-validation. This method maintains the class distribution across each fold, ensuring that both the training and validation sets are representative of the original data. This is particularly useful when certain categories are underrepresented. Once we've chosen a validation technique, how do we measure the model's performance? This depends on the type of task. For classification problems, common metrics include accuracy, which measures the percentage of correct predictions. While accuracy is a good starting point, it can be misleading when dealing with imbalanced datasets. For example, if only 5% of voters abstain from voting, a model that always predicts voter would be 95% accurate but completely useless. In such cases, we turn to metrics like precision, recall, and the F1 score. Precision tells us how many of the predicted positives were correct, while recall measures how many actual positives were identified. The F1 score balances these two, offering a single metric that accounts for both false positives and false negatives. For regression tasks, we use metrics like mean squared error MSE or mean absolute error MAE. These measure the difference between the predicted and actual values, giving us a sense of how far off our predictions are. It's also important to evaluate multiple metrics, especially when optimizing models. A single metric can't always tell the whole story. For instance, high accuracy might hide poor recall, which could be critical in certain applications. Finally, let's discuss some best practices to ensure effective validation. First and foremost, avoid data leakage. This happens when information from the validation set inadvertently influences the training process. For example, if features in the training data are derived from the validation data, your model might appear to perform well but fail on truly unseen data. Another best practice is to shuffle your data when splitting it into training and validation sets. This ensures a random distribution, reducing the risk of biased splits. For example, if the data is time-ordered, a non-random split might place all recent data in the validation set, leading to skewed results. Lastly, ensure that your validation set is large enough to provide reliable performance estimates. A too small validation set can lead to noisy metrics that don't accurately reflect the model's performance. In summary, effective validation is critical to building robust models. By using appropriate techniques like holdout validation or k-fold cross-validation, selecting the right metrics for the task, and following best practices, we can ensure our models perform well on unseen data. In our next lesson, we'll discuss how to use test datasets for final model evaluation and deployment readiness.